Question 11 from the 2025 Higher Physics Examination Paper 1. A proton, which is a positive charge, enters a region of magnetic field as shown. The direction of the force exerted by the magnetic field on the proton as it enters the field is given from the following responses. Now we can use our left-hand rule for that because we know that the proton's a positive charge, and we use the phrase of Elvis Presley as Elvis left the building. We use the left hand. We're positive he's left the building. You can check that out on the notes. So the proton, we use our left hand for the positive charge. It's going to enter a magnetic field which is pointing into the screen. So your first finger, you point into the screen. Your second finger, you swivel round until it's pointing down the page because that's the direction the proton is taking. And your thumb should be pointing towards the right hand side of the screen. So our answer is that the proton will be moved towards the right of the page, and we can see this in a little diagram here. We can see a simulation from the website I have. You can see the positive charge, the blue dot representing the positive charge, enter the magnetic field and being swept away to the right hand side of the page, and we can practice using our left hand rule to get that right. So the answer for this question here is that it's going to be moving towards the right of the page, and the answer is E. Question 12. The following statement represents a nuclear reaction. You have radium on the left hand side with a mass number 226 and an atomic number 88, and that decays to give you radon, which has got a mass number of 222 and an atomic number of 86, and you've got to identify what the element X is. So all we have to do is compare the mass numbers on the left hand side and the atomic numbers on the left hand side with their corresponding mass and atomic numbers on the right hand side. So let's do that now then. So we start off with radium, it's going to give you 226 and it's going to give you 88, and that's going to decay into radon, which is Rn, and it's got a mass number of 222, and the atomic number, always in the bottom, is the value of 86. So we've got this element here, X, and we know that the mass numbers must add up. So we've got 226 here, 222 there must be a 4 there to balance the equation. 88 for the atomic number, 86 the right hand number, so there must be a 2 there. So we've got an element or a particle with a mass number of 4 and an atomic number of 2, and that particle is in fact an alpha particle. So an alpha particle is the following. We can write it as alpha 4 and 2. Remember, it's got a 2 plus, but we don't need to worry about that right now. So we're looking for 4 and 2 to be an alpha particle, and the answer is A. Question 13. A small lamp is placed 0.40 metres from a light meter in a darkened room. You can see the diagram there. The radiance of the light from the lamp is measured using a light meter. The radiance at this distance is 20 milliwatts per metre squared. The light meter is now moved until the radiance is 80 milliwatts per metre squared. SQ is just left off that wee minus sign between the two. The distance between the lamp and the light meter is now, and you're given the 5 responses. Okay, we use our radiance equation as found in our relationship sheet. The radiance I is equal to a constant number divided by d squared. D being the distance between the light source and the small lamp. If we cross multiply, we get I d squared is going to equal to a constant number k. Now what does that mean in practice? It just means that no matter what the radiance is and the distance, we multiply the radiance times the distance from the light source squared, you should get the same answer. And that means we have the first radiance I1 and d1 squared, and that should equal to the second radiance times d2 squared. So we'll set up our equation from that then. Remember, we're after d2 squared here. The first radiance is going to be 20 milliwatts per metre squared. So we can leave out the units and just put in the value because both sides will contain the same units and they'll cancel out. So we're going to have 20 times d1 squared. Now d1 squared is going to be 0.4. All squares is 0.4, and it's going to be all squared. And then that's going to equal to the radiance I2, which we've now gone up to 80, and times d2 all squared, d2 all squared there. So 20 times 0.40 all squared divided by 80 should give us a value for D2 squared. Now we do that in our calculator, we end up with the following answer. We end up with D2 squared is going to equal to 0.04. So therefore D2 is going to equal to the square root of 0.04, and therefore it's going to equal to 0.2 meters. So our new distance is 0.2 meters, and that makes sense because you're bringing the radians up, therefore you must be coming a lot closer, and therefore we can see that the answer is going to be 0.2 meters, and the answer to this one is going to be C. Question 14. A student sets up the following apparatus to investigate photo emission from a zinc plate. You can see we have the glass tube which has been evacuated from it with air, and it's a vacuum, and we have the zinc plate inside that glass tube, and the zinc plate is connected to the positive end of a battery and our ammeters in series. And what we're asked in this question is the reading on the ammeter can be increased by, well, we know that when the light shines on the zinc plate, photoelectrons will be released. And the question really asking is, how can we get more photoelectrons from the zinc plate over to this side of the metal plate here, so as we can have this current registered here. Now to explain this fully, I'm going to go to the PHET site to show you a simulation of what's happening. So let's look at the PHET site. Very similar situation. You can see that this part here is going to be the negative part of the battery. The simulation has got the battery really wrong way around. In fact, this is the negative part of the battery here, and that's the positive part. And you can see that plate there is going to be negative, and this plate is going to be positive. Now, we'll go through each one in turn. Once we increase the intensity of the ultraviolet light, we can see we're going to get photoelectrons emitted. But because the other plate is negative, the photoelectrons can't really reach it because the electric field is actually in the opposite direction and is actually pulling them back towards the zinc plate. So let's go through each one in turn then. We want to find out more current passing through here. So the first one is replace the ultraviolet light with visible light. Well, we can do that. We can go to ultraviolet light and we can go to some visible light, and you can see it has no effect on the current. In fact, it makes the current still zero because no photoelectrons are emitted from the zinc plate. The second suggestion is replace the ultraviolet light with infrared. So we can go to infrared light, and once again we don't get any photoelectrons emitted because zinc has got its threshold frequency in the ultraviolet range. So go back to ultraviolet and we can see we're getting the photoelectrons emitted. Now the next part says decreasing the radiance on the zinc plate. Well, if we decrease the radiance, make less light shine upon it, you can see that we're still going to get electrons released from the metal plate, but they're going to be a lot fewer. That's not going to affect the current either. So we go down here like that, and we can see even tiny amount of light shining on it is capable of releasing photoelectrons. Remember, in this simulation here, those photoelectrons with the maximum energy are the ones that go further. Now the fourth suggestion is reverse the battery voltage. So if I put the intensity up again to get more photoelectrons emitted, if I reverse the battery voltage, switch it round, wow, yeah, now you get the current increasing, because when you reverse the battery you have made this plate positive, which attracts the electrons over, and therefore you get the current. The final statement there is allowing air into the glass tube. Well, if I allow air into that glass tube, the electrons are not going to get near that plate here because they're going to bump off the air molecules, so that's not a proper suggestion. So the answer to that question is you simply reverse the battery. So go back here again, and it says here the reading in ammeter can be increased. We just saw that by our demonstration by reversing the connection on the battery. In this case, this battery here was minus, because that's the minus sign and this was the plus sign here, but if I reverse the battery, then I'm going to get this side to become plus, and that will attract the electrons over. So our answer for question 14 is D, reversing the connection to the battery. Question 15. Ultraviolet radiation of wavelength 250 nanometers is incident on a metal surface. The work function of the metal is 3.1 times 10 to minus 19 joules. the energy of each photon of ultraviolet radiation is, and you're given the 5 responses. Now, the distractor in this question is the work function, because we don't really need it. What we're asked to do is find the energy of a photon of this ultraviolet radiation, and we're given its wavelength. So we do know from a relationship sheet that the energy of a photon E is equal to Planck's constant h times the frequency of the light. Now we can change that to the sister equation, because we know that the frequency of the light is equal to the speed of light divided by the wavelength lambda. So we can change E to give the sister equation h times c divided by lambda. Also a very useful equation to know. So to find the energy of a photon, if we know its wavelength, we just have to use this formula here. So energy E, Planck's constant, 6.63 times 10 to the minus 34, multiplied by the speed of light, 3 times 10 to the power 8, put that in a bracket to contain it, and we're dividing that all by the wavelength, which is 250 nanometers, which is 250 times 10 to the minus 9 meters. So we do that in our calculator and go to two significant figures. We get an answer of energy of the photon equal to 8.0 times 10 to the minus 19 joules. And that's going to give us the following response here, D.